Ik heb nog niet alleen mijn slides getest, maar het komt denk ik wel.
Ja, dus Max, jij kan een introductie geven en dan kan Pien de slides erbij halen.
Oké. Ten eerste wil ik iedereen welkom heten. I'm going to switch to English because we have a committee, an eminent international committee and one of the reasons that I am not available there is because they are, of course, very pressed for time, and this is the one moment we can do that and put her committee together. So I want to wish you all a welcome. I cannot really see you, but I'm assuming from the background noise that the room is full of aficionados of the work of Pien van der Berkmortel. So really, this is one of the, for me, this is the, I regret not being there because this is always the greatest moment for me, at least, in the career of a student. It's the moment it all comes together and a thesis is presented that exceeds even the student's own imagination, what he or she could have done. In this case, of course, she. And but nevertheless, let me continue why I'm so glad to be here is what Pien is going to do is what Pien did is she is part of the economic engineering group here at this Delft Center of Systems and Control. And economic engineering sounds like it's about economics, but it really is mostly engineering. So that's to the great disappointment of those who might be interested in economic theory. But it is in using engineering tools to model economic systems. Now, the engineering tools we use in this department are all about the dynamics of things, how things move. And the emphasis of the economic engineering group is then also on how things move. And in Pien's case, is about the motion of different modes of energy, like clean hydrogen, this hydrogen, gray hydrogen, wind energy, etc. And how these all can come together, not only how they move physically, but also how the prices move and how they adjust. And this is the topic that she's going to be talking about, and she is way more suited than I am to talk about it. So with that, I'd like to end my introduction and invite Pien to start her presentation.
Yes, thank you, Max, for the introduction. Perfect. Welcome, everybody. It's very nice to see so many people here. Today, I'm going to show you the potential of economic circuit theory for the modeling, the design, the analysis, and also the control of a spot market for hydrogen. Our energy landscape is currently going a transformative shift toward a zero-emission future. And as hydrogen has the potential to decarbonize industrial processes, the Dutch government sees high potential in the development of a hydrogen economy. And to make this economy future-proof, we need to increase our renewable hydrogen supply. And therefore, we need renewable hydrogen projects, such as the Holland Hydrogen One in Rotterdam. But therefore, we need to make it easier for these projects to determine if their investments are worth it. The current market for hydrogen is dominated by locally produced hydrogen using natural gas. And this hydrogen is traded through long-term contracts with fixed prices and fixed quantities. And these contracts, these ensure a predictable revenue stream for hydrogen projects. However, the problem is with this market that it's difficult to integrate large quantities of renewable hydrogen, as both the prices and the quantities are difficult to determine. And as you see here in the snapshot from the HyClicks, it's a hydrogen index of past month. There you see that the marginal cost of low carbon hydrogen is very constant, while the marginal cost of renewable hydrogen fluctuates. To integrate larger quantities of renewable hydrogen, market experts envision a spot market for hydrogen, similar to a spot market for natural gas. And in such spot market, the prices become dynamic as they react to fluctuations in supply, demand, and also storage levels. But this market will allow us to balance supply and demand in real time. However, this market has some limitations as well. And there are two main limitations, and that is that because of the dynamic prices, revenue streams become more unpredictable and it's more difficult to determine the revenue streams for hydrogen projects. And also because of the dynamic price, we will see an increase in volatility in both supply and prices. And therefore, I will demonstrate you that economic circuit theory addresses these two problems, as we can build this supply and demand driven pricing mechanism directly into our models. I'll also show you how we can incorporate price effects of different coupled energy markets. And also, we could also use economic circuit theory for the design of the hydrogen market. However, this can be found in my thesis. I will talk about it less today in my presentation. But for example, we could include an extra ammonia market. I'll show that with dynamic scenario analysis, which is a technique within economic circuit theory, we can address the unpredictability of hydrogen flows and prices. I'll show you that with our simulations, we can directly derive the time evolution of energy prices, storage levels, but also of the energy flows. And what we can also do is we can test the dynamic resilience of our markets, which is very important, in particular for new emerging markets, that they react stable to, for example, an offshore wind energy shock. Then I'll show you, after showing you how the volatility of our market, that we can also minimize the volatility by implementing regulatory intervention using control theory. The hydrogen spot market will operate on the hydrogen backbone, and therefore this will be our blueprint of our economic network models. The hydrogen backbone will physically connect the 5 largest industry clusters in the Netherlands, and here you see all kind of market agents that will be connected to it. Those include various suppliers, industrial demanders, but also storages and wind farms. And I've been to Tino, and they use this network to determine the flow of hydrogen through the backbone. However, what they do not see is that we can also use this network to determine the economics in the hydrogen spot market. And this is what we're going to add with economic circuit theory. Here, this is what we call the node structure. We will use this structure to determine the flows of hydrogen. But more importantly, we introduce a so-called mesh structure. And I've visualized it here as the suppliers and demanders that communicate their incentives to a market operator, which in turn matches supply and demand by adjusting the hydrogen price. And by exploiting these two structures, we are going to look at this logistics network as an electrical network. Here do you see such an electrical network. And this network does not only reflect the distribution of hydrogen, but also the balancing of incentives among the market agents. And we model the same market agents as you see at the past slides. Those can be found here. On the left, we model 4 different hydrogen supply chains, which include liquid hydrogen import, gaseous hydrogen import, renewable hydrogen production, and also low carbon hydrogen production. Here on the left, you see a liquid hydrogen market and also a natural gas hydrogen market incorporated in this model. And we couple this market using mutual inductance. And this is what reflects the price effects between the different markets indicated here. On the right side, we have the different industry clusters in the Netherlands. And looking at their demand, which we you see over there, that's what we call an inductor. And this is a very important element, as this is where we can read off the hydrogen prices. Then in the middle, then here at this dot at the top, this is where supply and demand come together. If there's any excess flow, this excess flow is brokered by the market operator and is stored or extracted from the central salt caverns and this element. And this is where we can measure our storage levels. And then the market operator, this matches supply and demand by putting market friction on the market. And then here on the left, this is where we include or generated offshore wind energy. And this one is a regulated current source. So we can determine what our wind input is going to be. I'll show you how we can explicitly derive both the energy prices and the storage levels from this electrical network. And we do that by exploiting the two structures I showed you before. Here you see the blue dots. And here I've indicated two meshes, but these can be found in the whole electrical network. And by using a node and a mesh law, we can derive a so-called state space representation. And this state space representation tells us exactly how energy prices and storage levels change over time. The upper one is the state matrix and the lower one is the input matrix. And I've structured them such that you can recognize the 4 different energy markets. Here on these diagonal blocks, those show us the internal market dynamics of each energy market. And we can see that on the off-diagonal entries of this matrix that the stocks and the prices within each market are coupled. And also on the diagonal, we see that the prices within each market also influence the price dynamics. On the off-diagonal blocks, we see how the different markets are coupled through the price effects using the mutual inductance I showed you before. But let's focus on the hydrogen price because that's what we're interested in. Here we can see that the hydrogen price is influenced by the price of liquid hydrogen, the price of offshore wind energy, the price of natural gas, but also on the hydrogen price itself and also on the storage level. But here we see that it's also influenced by the rate of change in offshore wind energy generation. Okay, so I'll just show you the analytical representation of a model, but we're going back to a graphical because then you see what's going to happen. And now we can test the dynamic resilience of the market. And what we do, we will put an offshore wind energy shock on it and see what is going to happen. And such a shock would represent, for example, a winkelflout when there's no wind, or when, for example, wind parks are in maintenance. So it's really interesting to see what happens to the market price. So we put it here in our model, in our current source. Now we're going to measure what our different supply chains are going to do and how our prices are going to react. And from our measurements, we can derive the time evolution of our hydrogen supply chains and also of the energy prices. And what we see here on the left is that the renewable hydrogen supply in green is directly affected by the shock, as you would expect. But it also has an influence on the other supply chains, and that's because as a result of this decrease in supply, we will see here that the hydrogen price in blue rises directly and causes volatility. When prices rise, suppliers want to supply more. So this is why the other supply chains decide to supply more. And this will in turn affect the prices of liquid hydrogen a natural gas. But what we see, the natural gas market is larger and it's more flexible. So it has a less impact on the natural gas market, while the liquid hydrogen market is not that flexible because of imports. And it's also much smaller. And that's why we see that the price of liquid hydrogen is highly affected by such a shock. Okay, so now I've shown you the volatility of this market. And now I'm going to show you how we can also minimize this volatility. And we're going to do this by designing a regulatory intervention. And this is what we will see in new markets, such as the hydrogen spot market. And for example, let's say we have a budget of 10 million euros, of which you want to design a subsidy scheme. And as low carbon hydrogen, as I showed you before, is a really flexible supply chain, we use that one in our subsidy scheme. So what we do, we implement a regulatory agent. And what this does, it one measures what the incentives and what the rate of change in price is doing. And depending, and we compare it with our reference, which we set to 0 as we want to minimize our volatility. Then it's going to determine, okay, how much low carbon hydrogen do I need to produce more such that we can reduce this volatility. And I will model this as what we call a PID controller. And I've chosen so because the control actions of this controller can be made economically interpretable. So looking at this regulatory agent, the control actions of the regulatory agent are split in a proportional, an integral, and a derivative controller. So what this does is, here we look at the error of the incentive, so the rate of change of price, and we want it to be 0. But if it's not 0, there we have an error. And what the proportional control action does, it relates this error directly to a flow of low carbon hydrogen. And yeah, as you can see, you can think of it as a knob and tune it such that you can minimize the volatility. And what this action does, it creates market friction, and as a result, it minimizes volatility. So by increasing the gain, we can minimize the volatility. Then the integral action, that one integrates the error. So while this is an incentive, which is a rate of change in price, the integral is a price. And if we relate this one to a flow, we can look at it as an elementary supplier. So by increasing the control gain of this control action, we increase the total of subsidized low carbon hydrogen. Oh, nope. Then we also have the derivative control action. And what this one does is looks into the future. It anticipates on what is going to happen with our incentives, so with our rate of change in price. So by looking at the acceleration of it, and relating that one to more or less low carbon hydrogen production, it anticipates on what the market is going to do. So now I'm going to show you the effectiveness of this controller. And I've tuned these gains such that this controller is realistic, that and it stays within the budget of 10 million euros, but also that the control action, so the extra or less subsidized low carbon hydrogen, is a realistic amount that it can be scaled up or scaled down in our production. So what we're going to do now, we're going to put a wind sequence in it. As you can see, it's a measured wind sequence. And specifically, we're going to look at a period which is very volatile in wind. Again, we're going to measure what our supply chains are going to do and what our prices are going to do. Here we have selected a wind period in winter with a high variability in renewable hydrogen, as you see in green. You can see that the subsidy scheme results in more volatile low carbon hydrogen supply, which is indicated in the blue dotted lines. What you also see is that it shifted forward, that it anticipates on what is going to happen with the renewable hydrogen production. And as a result, we see that hydrogen prices are becoming less volatile over there in light blue. Then the other supply chains will react, and those will become less volatile as well, which we see here. What we do, what you also can see here is that we see a slight increase in natural gas price, and yeah, what you would expect because we're producing more low carbon hydrogen, so we need more natural gas to do so. Looking at the total hydrogen supply, we see that this subsidy scheme slightly minimizes the volatility of this supply chain. And an advantage of economic circuit theory is that we can measure all these, so we can quantify what the effects of our subsidy are. So the average hydrogen price decreased with 2%, while the supply increased with almost 1%. But we have to cope with a 3% increase in natural gas. And this is just with a bit more than 9 million euros per year. But imagine if you have a budget of even more, what we can do with that. And the subsidy costs are just 3% of the total hydrogen trade in the market. So in conclusion, you could say that what I've shown you is a proof of concept of economic circuit theory. And that with economic circuit theory, we can effectively address the supply and demand driven pricing in a spot market for hydrogen. And with our models, we can make revenue streams predictable, with which we can support investments in hydrogen projects. But also, we've seen that we can quantify the volatility in the market through our dynamic scenario analysis, but we can also minimize the volatility by implementing regulatory intervention. But we can also use this model to design a regulatory intervention in a way that we get desired energy prices. Then I've showed that we can derive an analytical state space representation, which precisely describes how our prices and our storages are changing over time. But for further research, the state space can be used for even more, for building more complex controllers, but also for system identification. And what I've showed you is just a prototype, but we can do so much more with it. We can add extensions as we have a modular framework, so we can add the ammonia market, as I told you, but we can also add whatever market we want. And we can build more complex agents using the recent, even more recent port-based approach. It's an extension of economic circuit theory. And an advantage of this approach is that we can also take our analysis to the Laplace domain. And what we can do there, we can do analysis that are not apparent in the time domain, including the seasonality in storage and in trade. But where I see particularly an opportunity is in optimizing the wind hydrogen production strategies, using, for example, model predictive control. And therefore, we need to include an electricity market in our network, and also a predictive model of wind energy. And with this, we could optimize a strategy such that wind hydrogen supply chains become more profitable, but also, as we see that the offshore wind generation and the hydrogen production has high influence on the hydrogen price. By optimizing this production strategy, we can also minimize further the volatility in the market. So now we should build a toolbox using economic circuit theory, which we can use to further exploit its potential for not only spot market modeling for the hydrogen market, but also for energy subsidy modeling in general. Thank you.
Nee, laat je slides maar staan. So do we have any questions from the audience?
Mag ik in het Nederlands doen? Want mijn Engels is
Ja, hoor.
behoorlijk minder dan wat van Pien, dat mag duidelijk zijn. Pien, dank je voor je heldere uitleg, voor dit zeer complexe en actuele onderwerp. En heel mooi om te zien hoe een economisch vraagstuk zo met slimme Delftse techniek kan worden benaderd. Dank je wel. Maar mijn vraag is, in die scenario-analyse laat je zien dat een plotselinge dip in de hoe heet het?
Offshore wind.
In die offshore wind, ja. Dus dat die een enorme schok in het model veroorzaakt, een enorme volatiliteit.
Ja.
Zou je heel makkelijk bijvoorbeeld weersverwachtingen of planbare maintenance in je model kunnen opnemen, waardoor je dat effect minder maakt?
Can you hear online? Otherwise, I will repeat the question. So, the question is, can we implement like weather forecasts into our model to make predictions better? And indeed, we can. Yeah, I only implemented, I added a measured wind sequence, so it's deterministic. But indeed, we can extend by incorporating forecasting models for wind, but not only wind speed, but wind direction, because those all have influence on the offshore wind prediction. But those are all further work, but yes, we can, and those can be used, for example, in combination with the model predictive controller, which uses these predictions to optimize strategies. So we can incorporate the forecasting, but we can also exploit the forecasting to make the strategies better.
Dankjewel.
Further questions?
I have a question. So it isn't clear to me, and that's probably more my problem than anybody else, but the application against an electrical network and using the analogy of an electrical network as a framing tool for the economic circuit theory. Why does it require that economic network sort of comparable? You could have picked any kind of economic model where you measure supply and demand and the shocks that.
Very good question.
Very basic, but.
So I'll repeat it for the people at home. The question is, why do we use economic circuit theory in the first place? And indeed, what you say, we use an electrical an analog to model economic systems. And what the main contribution is of economic circuit theory is that we incorporate price dynamics, but I'll try to don't go too deep in the theory of economic circuit theory, but we look at systems in the same way as engineers do. And in engineering, we have forces that drive in an electrical circuit that the voltages that drive why our current is flowing. And by exploiting this analogy to economics, we have the incentives which determine how the prices are driven up. So we can exactly determine why prices are going to rise and also how these prices influence our energy flows. And this is something current economic models just can't do.
Mm-hmm.
And this is why we use economic circuit theory in the first place.
Any other questions?
Het is de toekomst van, ik zag subsidieprijzen op de uitkomst. Dat varieerde nogal en dat was aanzienlijk, hè? Zo ergens 9% boven de, zeg maar, de energieprijzen. En ik snap wel dat er allerlei factoren zijn die dat gaan beïnvloeden via jouw model. Maar hoe kijk je nou naar die toekomst? Er wordt nou een fabriek gebouwd daar, ergens aan het zand. Als je zo'n model nou ziet, dan schrik je toch wel even dat het verschil met de orthodoxe prijzen, dat die toch nog wel een behoorlijke opstap vergen, die subsidies. En dat maakt het natuurlijk toch wel weer een beetje twijfelachtig of je dat full scale in moet gaan. Hoe kijk je daar tegenaan?
Yeah, so I think I will summarize your question as there is a lot of uncertainty and it's expected that prices are going to be higher. De verwachting dus dat prijzen hoger zijn en dat er nog heel veel onzekerheid is. So that is why we do need regulatory intervention, these subsidy schemes. But as you see, hydrogen prices are going to be volatile, going to fluctuate, and also going to peak to very high values. And as we already also know, is that building a factory is really expensive. So this is indeed what is holding people back from investing in renewable hydrogen projects, because they don't know if they're going to earn it back. And that's why we want to model it, see, okay, can we predict our prices? So can we make a calculation such that we can see if our investment is worth it? And we can also see that indeed subsidy is really important to influence prices. Now I just showed you a really minimal impact subsidy scheme, but those can be taken much further and in such a way that hydrogen prices are going to be lower. And this is going to be interesting for the demanders. But if subsidy schemes can also support suppliers, and if we know how those are going to look like, then this gives an idea if what is possible in the future. So there is just a lot of uncertain, and especially government support is one of the important factors in developing a hydrogen economy. So
Ja.
until we don't know what is going to happen, we don't know, but we can now at least test it. And
Kan je dan concluderen dat dit is ook weer een vorm van energievoorziening, van supply? Dat gaat naast atoomenergie, dat gaat naast zeg maar hoe heet het, de ouderwetse energie, hè, de fossiele energie. Dat we hebben toch al die bronnen nodig. En dat gaat het supply dus of jouw schema ook wel erg beïnvloeden. Dus als je al die bronnen nodig hebt, dat betekent dat ze allemaal doorgaan. Ook dit.
yes,
Dus die ontwikkeling krijg je dus op dat gebied, op dat gebied, op dat gebied. En bij elkaar maakt dat straks een energieprijs. Mondiaal. Mondiaal een energieprijs. Ja, dat heb je zover ben je nog niet gegaan om dat te gaan.
no, so indeed there are so many of energy, and we need them all for our future.
Yeah.
And it already has shown that hydrogen can be combined with, for example, the kerncentrale. Sorry,
Ja.
completely forgot the word. And we can produce hydrogen from electricity from the kerncentrale.
Nuclear
Yeah.
power.
Of course, yeah. To produce hydrogen. So there's an opportunity, but we want all kind of energy so we can balance everything, because everything is going to be volatile, especially when there are more renewables. And indeed, that will influence our prices, but by having more flexibility in our energy and in our markets, we can cope with fluctuations in supply and demand, and therefore we can also influence our prices. So it is just really important to combine it all. And indeed, I didn't show them all today, but
is coming.
But it's coming. We can include every market we want in such a network. So maybe for future research.
Thank you.
Pien, thank you so much. I learned a lot, and I have lots of questions, but one for me is like, I really noticed how you indeed, brought the peaks and the troughs, made them smaller by using the economic circuit theory. My question to you is like, who is going to use this? It's like, is it the people who build the factory, or is it the government? It's like, where do you see the use?
It can be used by everybody who has an economic interest, in this case for the hydrogen spot market, but in energy systems in general, because it can be used, as I told you, for example, further for optimizing strategies, but it can be used to also determine investment decisions for, shall I invest in storage? Because storage will, if the price is high, I'd rather get it from my storage. But for every regulator or other stakeholders, this model could be interesting because it gives you insights in prices, something that it isn't there at the moment. And for example, I've been to TNO, and what they have a model with some expected demand and some expected supply, and with hundreds of equations, they determine what the price are going to be, but they use prediction costs. And this is just another way to look at it. And by having more of those models, we can get insights in the behavior of a market that does not yet exist. But the main advantage of our model is that we can really see what the dynamics of our prices and of our storage are going to do.
One last question,
Kan online kijken.
online maybe.
Geen idee hoor, of er iemand is. Nee, volgens mij niet.
Hebben jullie helaas
I have
tijd?
one fun question. What did you like most about the thesis?
Oeh.
We did a lot of things. Modeling, you design the network, you control the network. What did you like the most?
I do think I like the modeling part the most because you can be creative there and you have like a whole toolbox. I use Simulink here, and you have like the electrical network components that you can connect to each other and put all kinds of things in it, and like a playground. But yeah, that excites me the most, just to see what is possible. And that's where I started with. But I see for the future, I would say building more controllers, because that's of course what we do here at System and Control.
Okay, let's thank Pien one more time.
Yeah, thank you very much, Pien. I think it's time, and Koen can point it out, is to end this part of the exam. What we'll do now is we're going to ask the audience to leave and take place in the, where is it? In the social room or in the Wiener room? Huh?
Social.
Yeah, you can wait in the social room. And the committee will take a little while, maybe 45 minutes or so, to go through the defense part. And then afterwards, when the white smoke comes out of the chimney, we'll all go up to the Wiener room, and I virtually, and we'll wrap it up. So probably you would need to, Pien, make a connection through Teams or something. Okay.
Ja.
Zo, als je dat wilt doen, als je via Teams een andere verbinding maakt, zodat kan deze eventueel open blijven, deze Zoom-meeting, voor als we de wrap-up doen. Oké?
Ja. Koen gaat een meeting aanmaken als het goed is. Mijn laptop.
Ja, ik was nou zo via Teams mode.
Ja. En dan moet ik jou ook vragen, Pien, om naar buiten te gaan, eventjes. Dan gaat de jury een kort beraad voeren en dan word je door Koen naar binnen gehaald. Oké? Laat alles gewoon lekker staan.
Was er een computer bij? Oké. Ja, dus kan ik daarin meelopen? Oké. En dan kom ik hier. Dankjewel voor de goede vragen. Ik lijk het je allemaal.